Hello, and welcome to this talk entitled Tiffin and MGen, an expressive policy language with multiple runtime monitoring tools. My name is Zach Fry, and this material was originally prepared for HCSS 2022. So to start off, just a brief outline of how this talk will proceed. First, we'll go through the problem statement and state-of-the-art tools in this area. Next, we'll introduce the Tiffin policy language, followed by the MGen model generator. And then we'll go through a series of deployment use cases to highlight the various features and protection mechanisms provided by these types of tools. So in terms of a problem statement, I think it's well known that in spite of heavy investment, cyber attacks are an increasing threat. They cost trillions of dollars to industry and government alike every year, and increasingly target more high-value deployments, including defense agencies and large tech companies. In addition to this, software itself is increasingly more complex and mission critical, and it uses interconnected systems, varied deployment frameworks, and so the attack surfaces are increasingly complex and diverse, which makes it hard to provide protections for all possible threats. Additionally, zero-day exploits are increasingly common as well. These include ransomware and insider threats. In this way, we struggle to keep up with modern and complex attacks, and essentially modern security practices cannot keep up with current and emergent cyber attacks. So this is the problem. To go a bit into the state-of-the-art techniques in this area, so we'll be mostly covering cybersecurity tools like anomaly detectors and runtime monitors in this scope. So that's what we'll be sort of working through on this slide. There are several common limitations and restrictions to these existing tools. For instance, pattern matching tools essentially try to identify known bad patterns that we've seen in the past. The problem here is that they require constant updates to keep up with all of the attacks that are emerging, and also have limited zero-day capabilities. That is, they don't often do well identifying attacks that they haven't seen before. Additionally, many of these tools have domain specificity or limited scope. So based on the underlying mechanisms that are used, they may only be applicable to specific types of systems or specific types of faults and errors and vulnerabilities. Thus, to have a complete protection strategy, one might have to employ prohibitively many of these tools. Additionally, some tools have limited mitigation capabilities. That is, they mostly provide information based on identifying these faults, but then pass the burden of fixing them off to the user. And so by providing only limited forensic evidence, it can still be quite a manual effort to stop the problem once it's identified. Additionally, a lot of these tools require considerable human effort. That is, to design and deploy the protections. It requires manual specification or instrumentation, which of course affects scalability and also can cause problems in terms of code evolution or system evolution. So to this end, we introduce Tiffin, which is the language we've developed for enforceable runtime policies. So the key mechanism here is that Tiffin defines correct program behavior and correct program state over critical points in individual programs. So rather than doing something like pattern matching, which we've described in the previous slide, we simply define exactly those things that the program can do, and then any diversion from that may be considered a potential attack. Additionally, Tiffin provides an autonomic solution. That is, it both identifies and mitigates known and unknown attacks. So again, providing sort of in-the-moment, real-time solutions to stopping attacks as well as identifying them. So there's several insights here. First of all, we outline correct behavior rather than known bad patterns. So this allows us to guard against unknown attacks. Second, we build per program models, so it's not one size fits all. Everything's a nail when we have a hammer. So this allows us to be generalizable, but also customizable based on the individual functionality of the program or even the program in your specific deployment. Additionally, Tiffin provides diverse specification mechanisms, so a wide toolkit. And so this allows us to be flexible and also performant, again, taking into account what the environment in which a program will run might be like. And finally, it defines context-specific and deployment-specific behavior. So this allows us to take the customization even one step further, again, identifying specific behavioral patterns and allowable program state within an individual environment. So maybe one instance of a web server runs different than another instance depending on the needs of the users, and so we can account for that fully in the policies we provide. So as mentioned, Tiffin is an autonomic toolset. That is, it provides capabilities for both identifying and mitigating threats in real time. On this slide, we'll go through some of the identification mechanisms, the policy behavioral specification tools that we use. So first off, we have program invariants. So these allow for things like checking that a valid server response exists before transmitting information. So just an example of one of the many types of invariants that you may see in practice. The second mechanism is state machines. So this identifies sequences of events and also potentially program state that must occur to constitute valid program behavior at runtime. So this could enforce something like ensuring authentication happens before a protected action occurs, again in a web server. The third mechanism we provide is memory safety mappings. So this is for a given part of the program, it can only access a certain swath of memory. This can be used to guarantee consistent module write patterns, make sure that something like a Trojan isn't writing to memory that it shouldn't be. And finally, this is sort of a bit of a different departure here, but we also provide capabilities for fuzzing. And so here it would be something like testing for unexpected values and user-supplied data. And so those are the major threat identification mechanisms. Now we'll go through the mitigation or corrective action tools as well. So we have several types. First off, we can alter the internal state of a program. So in the case that we see that maybe an attacker has managed to access private data, we could instead change the web server response for a malicious request to be something like a 404. So the data is not exfiltrated, and instead the web server continues on as it would have normally, but in this case, returns a 404 page rather than the actual, protected data. An additional mitigation type includes skipping instructions entirely. And so this would be, you specify exactly when a certain condition is met, you skip this many instructions. And so this could do something like avoid malicious writing mid-execution, then again continuing normal execution. So the idea here is to interrupt the normal program behavior as little as possible, but also still thwart the attack. A bit more drastic mitigation type would be to abort the program entirely. So this is perhaps a more sort of last-ditch effort, but could be useful in certain cases. In this case, like preventing information exfiltration during an active attack. So again, sort of higher severity corrective action, but again, could be useful in certain cases. An additional mitigation action could be to simply print a message. So this would be more of a debugging or like forensic type mitigating action, where we provide all of the available program state and execution sequence data that was happening as the attack occurred, so that you could piece back together sort of exactly what happened after the fact. And one future thing we're looking at includes returning from a function. So we've seen a couple of attacks that essentially send the program into an infinite loop. And so here, this would be a mechanism that allows you to exit that infinite loop whilst then hopefully resuming normal program execution. So as I mentioned, we're currently working on that, hoping to add it to the toolkit in the future. So those are all the identification and mitigation mechanisms. Here we show some example Tiffin itself. You can see on the top, the first two entities are instrumentation specifications. So these are events that happen in the code and exactly where they happen. So this lets us know, at runtime when we're performing the actual checking, where should we be doing that checking and what should we be looking at. You can see the first one includes a function entry in a C file and also a C expression, which is a string representing the user's IP address. So user IP is the actual C variable that occurs in the source code. So we're, again, mapping it directly to the code itself. The second one follows kind of the same structure, but in this case is a source line rather than a function entry. You can see we're on line 522 of serve.c. We again identify a variable that is in this case an int, and it's a struct field that also represents an IP. The third entity here is the action we're going to take in case something bad happens. In this case, we're looking again at a line which happens to match the protected access line above. And the action we're taking is to update program state. notably taking the ret code for the same struct and returning a 403. So it kind of mimics the example I just mentioned. On the bottom, we have the actual policy specification. In this case, it's a state machine. You can see we have two productions, the first of which goes from the start state to authenticate and then to protected access event. So this is the normal expected behavior. The second production represents the sort of alternative case where if we just go to the protected access action without authenticating, then we perform the block request action, which again returns a 403 rather than whatever the protected access execution would have normally done. So that's an example of what Tiffin looks like. Once we've defined our policy, we require a mechanism for creating an actual enforceable deployable runtime checker. To this end, we've implemented the MGen tool, which is the model generator. The mechanism here is to translate high-level specifications to low-level deployable runtime checkers, as I mentioned. There's a few insights surrounding this tool, first of which it has push-button automation. So if you feed it the binary and the Tiffin specification, it will spit out an actionable client. Helps for rapid deployment and usability. It also has integrated binary analysis, so the mapping from source level to binary level is sometimes non-trivial, but this allows us to generalize to arbitrary programs. It also includes multiple backends, which I'll go into in the next slide, but this allows us sort of flexible deployment options and wider deployability based on, again, the environment in which you're running the target program. And then also we have optional preliminary policy generation. So writing these specifications, as I mentioned on the limitations slide much earlier, can be a large human burden for the user. And so we have a baseline generator for easing the initial burden to the users and also potentially handling code evolution. So we'll spit out a baseline policy, then the user iterates over it, corrects things, makes things stronger, and then deploys that sort of iterated over policy. So what does MGen look like? As I mentioned, it takes the binary and the Tiffin runtime policy and performs binary analysis to map all of the source level information into binary level information, and then essentially using templated code identifies all of the internal mechanisms that make up the actual checking at runtime. And then creates a client for this set of possible deployment contexts. So the first one is Dynamo Rio, which is dynamic runtime translation. It's a little bit lighter weight than the second one, which is a hypervisor-based approach. And then finally, we can rewrite binaries to inject the actual checking and mitigation actions into the binary, the executable itself. So three options. Different performance implications, different flexibilities, but trying to provide, again, sort of a toolkit for a wide range of possible deployments. So one of the big challenges here is the actual binary analysis, the mapping from source to binary information. To this end, we've developed a sort of separate tool called Dwalin, which uses dwarf information that's baked into the binary at compile time. To essentially extract the binary mappings and perform the analysis that we require to identify things like where a given C variable lives at a given point in the program. And so you can see here we have an example on the right. Essentially here we're looking for the IP field in the rec struct, and we've given it an address in the program where we want to identify this, like where in the program execution this should be introspected. You can see on the bottom, we return something that looks like the base pointer plus 16 minus 176. And then we also have a specification for where the type address lives and the size of the type itself. So this is all useful information, again, for performing these mappings and providing the information to the eventual checking frameworks such that it can introspect the program state at the places we want to and return us values, allowing us to make the checks that we've identified in the Tiffin policy. In the future, we hope here to potentially integrate additional binary analyses to lift the dwarf requirement. But for the time being, and given the imprecision inherent in things like decompilation and binary analysis, we have stuck with dwarf up to this point. So now we'll get into some of the use cases for Tiffin. As mentioned, we have sort of 4 projects here. including 3 sort of monitoring applications and then 1 that is aiding in fuzz testing. So there's several considerations with each of these individual monitoring applications. For Linux apps or general purpose user apps, there's a wide range of functionality that we have to cover. So we, again, require sort of a sufficiently wide range of tooling to potentially identify policies that are relevant for all the possible attacks that would occur in these types of programs. The second is UEFI, which we'll get into exactly what that is later, but essentially it's part of the bootloader. Happens very early in the computing process, and thus there's limited monitoring options there. So we have to find a suitable backend. Third, we'll look at IoT devices. Here, of course, we have resource constraints. They're smaller than general purpose computers, and also potential connectivity issues where it wouldn't be able to send monitoring information back to a main hub. And so we have storage and communication considerations there. For fuzz testing, of course, this is a different type of protection. This is more testing rather than runtime monitoring, and so we have additional information needs and sort of have to modify the language to account for all of those possibilities. So as far as solutions to these problems go, for Linux, we have diverse and flexible specification mechanisms that I described in previous slides. For UEFI, we have bespoke hypervisor clients that specifically target the bootloading process. For IoT devices, we employ binary rewriting to get around resource constraints and also have very focused policies that perhaps measure less or enforce more narrow specifications on these devices to, again, sort of account for deployment considerations when it comes to edge type devices. And finally, for fuzz testing, we've added things to the language and have specialized clients to perform this type of testing and analysis at runtime. So getting into the actual use cases here, as far as general purpose Linux apps go, this is the general structure of how a deployment might look. So you can see on the top, we have all of our applications wrapped in monitors. The green arrow indicates these immediate mitigation actions like block request that we saw in a previous slide. All of this information produced by the monitors is then sent to the reasoning engine, or it could be sent to sort of a generic SIEM system or any sort of event aggregator. Then that can feed information to a UI for the visualization for a user, or more sort of system level actions can be taken here, like restarting a process if it seems to be deadlocked or something of that nature. Additionally, the reasoning engine might feed the forensic information to something like an automated patch generator or just the user itself for manual repair down the line. So that's kind of what the deployment looks like. We'll go over an example here. So for the NGINX web server is the target in this case. The assumed problem is that bots would probe public servers looking for known vulnerable modules and secure content. So simply stabbing in the dark to try to find things that it knows it can exploit, generally expecting to see a lot of 404s. So the autonomic solution here is to create a monitor that uses Tiffin internal variables per IP to count accesses to non-existent pages or content per connection. So that's the key here, is an attacker would again be probing over and over for things and receiving 404s, whereas a normal user would probably be using the website in the way you would expect. So if we can measure per IP counts that essentially tally up 404s, we can potentially identify attacks in this way. The mitigation action here would be to block these individuals, essentially blacklist an IP, from initiating requests entirely for a period of time. And it can then, if that threat seems to go away, it can then resume normal behavior. And in this way, it's, again, providing sort of an autonomic identify and react solution to the problem stated here. So for our second scenario, as mentioned, here we're looking at UEFI, protecting firmware in general. So some of the challenges here, we don't yet have an operating system. It is, in fact, what is loading at this time. There's also a single address space. The functionality is very limited. The work here is inspired by region-based write access control by Rebecca Shapiro out of Dartmouth. So UEFI is used on PCs, but also many other devices, so it's fairly ubiquitous. It's the interface between the OS and the bare hardware. Obviously, we're using the BIOS here, and UEFI itself stands for Unified Extensible Firmware Interface. Again, runs on many devices, is a part of many bootloading processes. So how do we protect this in practice? The policy strategy is to essentially use memory mapping. So we break it down into tuples of what, as in what code is executing at a given point, and where, which is where is the memory that it's accessing and potentially writing to. So you can see a sort of example mapping here on the top of this slide. And the policy is to essentially restrict, once we know what this pattern looks like, we want to restrict future executions to only access the memory that is accessed in the past. So in this way, if a driver memory access pattern or memory write pattern, very specifically, happens to be outside of the memory regions that it previously accessed, then we prevent that from loading, assuming that it might be a Trojan, for instance. And so this is, again, sort of a specialized mechanism, but you can imagine how this would be useful for general purpose Linux applications as well. So third-party modules, if your web server FCGI module is writing to internal web server data structures, that might be a problem. So you can see how this protection sort of generalizes in that way. Next, we'll take a look at IoT devices. So obviously there's many instances of IoT hacks in the news recently. We'll cover a specific one, happened to the Verkada Systems company. Essentially, a camera was exploited. I think they used default credentials to get into the camera, and then were able to access the full Verkada store system and exfiltrate video information for sensitive sites. So the IoT-specific deployment in this case uses binary instrumentation because we're deploying these, or we're trying to monitor things like cameras, routers, temperature controllers, GPS devices. So not things that have a lot of extra power to for instance, run something like DynamoRio or a hypervisor. Additionally, the monitors provide secured and distributed storage and communication for future forensics. These devices may not always be connected to some data store where we can send devices all the time. And so we have to devise lightweight ways to store the events and then also eventually communicate them with the sort of data store hub. The insights here are that devices with limited connectivity and on the network edge often require reflex responses. So something like block protected that we saw many slides ago in the Tiffin policy. If we wait until the monitor event information is collected, transmitted back to something that can perform an analysis, like a general purpose machine, and then it decides what to do and send it back to the device, the damage may have already been done in that case. And so we require these real-time autonomic solutions for protecting against these types of attacks on these devices. An additional insight here is that IoT devices typically have a very narrow set of effective functionality. That is to say, a camera might do, let's say, two things. It might capture video footage and then send it off to a data store. And so in that case, our behavioral policy can be comparably narrow, which allows us to cut out a lot of the attack surface if we're not really going to use a lot of the functionality in practice. So that's one of the sort of benefits of our approach in this environment. So we had a sort of baseline evaluation here. We mimicked this attack with commodity off-the-shelf hardware. The idea was that the attacker would rewrite surveillance configuration to additionally store footage offsite. So it would still get the data store normally on-site, but the attacker would also get a copy. And so the IoT protection here is to identify the normal behavior of the system. That is, it only ever writes to one single IP in normal scenarios. So the policy then immediately notices when the attacker leaks the feed to its IP and then effectively blocks that traffic. So again, allows us to immediately shut down the information exfiltration rather than simply identifying it and then the users have to pick up the pieces later. So the final use case here is policy-based component fuzzing. So thus far we've seen policies that protect programs at runtime, but in fact it's better to discover these bugs or malware or misconfigurations during testing, i.e. pre-deployment. So the idea here is to use the Tiffin policy to guide fuzzing with the underlying behavioral policy instead of just checking for correctness. So it's essentially a more fine-grained approach to traditional fuzz testing where the oracle that you have is the test passed or didn't pass. In this case, we can introspect individual parts of program state at various sites in the code. So it gives us a more, again, fine-grained or specific look into the program and exactly what it's doing. So the idea is to infer a metric against the policy to inform a fuzz testing mutator engine and then attempt to descend towards a policy violation instead of using something like test coverage, for instance. And so an example here that we've tried is on the ArduPilot bug. This is a drone autopilot software. And essentially the bug itself was that a speed variable should not drop below a given constant, or the cyber physical properties would essentially make the drone fall out of the air. And so it's very straightforward to express this policy and detect it in practice. You can see the sample Tiffin here. The instrumentation point at the top identifies the speed CMS variable as the param that we're going to be fuzzing. And then notably it's index 0 here, and then also the valid range is from 0 to 300. The idea, we then have a speed result as another instrumentation point, and you can see the actual policy on the bottom where we identify that speed CMS should never drop below this predefined constant in the code itself. And so the idea is that the fuzzer now knows the range for which it can assign values to speed CMS. It runs through things trying to essentially invalidate this invariant that we see, and thus we would have a counterexample that we could then use to fix the bug in practice. So again, a more fine-grained based approach to fuzzing rather than simply did the test pass or fail, which in this case would amount to did the drone physically crash or not. So that's our last use case at this point. Just as a recap, we've gone over monitoring and mitigation for general purpose Linux applications, also for UEFI firmware in the bootloading process. We've showed how autonomic protections for IoT can specialize to the constraints on those devices and those deployment environments, and then also shown how we provide automated support for fuzz testing. This concludes the talk. Thank you very much.